Assalamu alaikum dear students of class 11th. As in my last lecture, I have completed a chapter that was chapter number 12, magnetism, and today I am going to start a new chapter, that is chapter number 14, semiconductors. So let's see first which are the omitted subtopics of this chapter. So here we are having only one subtopic which is omitted for this academic year, that is point number 14.8, semiconductor devices, and in that we are having advantages and disadvantages. So this topic is omitted for this year. That means we don't have to study this topic, this subtopic. Apart from this subtopic, all the topic we have to study. So let's start with the introduction of this chapter. So basically modern life is heavily depend on many electronic gadgets. It could be a cell phone, a smartwatch, a computer, or even an LED lamp or a tube light. They all have one common factor, that is semiconductor devices that make them work. Semiconductors have made our life very comfortable and easy. Semiconductors are material whose electrical properties can be tailored to suit our requirements. Before the discovery of semiconductors, electrical properties of material could be of two types. That is what? Conductor or insulators. Fine. Now conductors such as metals have a very high electrical conductivity. For example, conductivity of silver is about 6.25 into 10 raised to of minus 7, whereas an insulator or bad conductor, insulator is also called as bad conductor, like glass, has very low electrical conductivity of order of like 10 raised to of minus 10. So electrical conductivity of silicon, that is a kind of a semiconductor, for example, is 1.56 into 10 raised to of minus 3, that we will discuss later on in this chapter. So this is what all regarding the semiconductor, fine, which we are going to study deep about this. So basically here, see, basically these semiconductor devices, they are small in size, consume low power, operate at low voltages, and have long life and high reliability. Even the cathode ray tube, that is CRT, which was used in television and computer monitors, which work on the principle of vacuum tubes, are being replaced by LCD. Nowadays we are using LCD TVs and LED TVs. So these that is the cathode ray tube, that is CRT. So it is replaced by liquid crystal display, that is LCD. What is the full form of LCD? Liquid crystal display monitors, which supporting solid state electronics much before the full implication of the semiconductor devices was formally understood. A naturally occurring crystal of galena, which was like lead sulfide with a metal point contact attached to it, was used as detector of radio waves. So that was this is only the introduction part of the semiconductors. So basically here the sub point we are having in your textbook, that is electrical conduction in solids. So electrical conduction in a solid takes place by transport of charge carriers. It depends on its temperature, the number of charge carriers, how easily these carriers can move inside a solid, which is the mobility, its crystal structure types, and the nature of defects present in a solid, etc. There can be three types of electrical conductors. It could be a good conductor, a semiconductor, or a bad conductor. So let's have a definition of all these three. So basically, first of all, conductors, which is also called as the metals. The best example of a conductor is any metal. They have a large number of electrons available for electrical conduction. A typical metal will have 1028 electrons per cubic meter. These electrons are called free electrons. Metals are good conductor of electricity due to the large number of free electrons present in them. So this is all regarding the conductors. This is the basic definition of the conductor. We will discuss this later on. Then insulator. So basically glass, wood or rubber are some common examples of the insulator. Insulators have very small number, that is 1023 per cubic meter of free electrons. Then semiconductors. So basically silicon, germanium, gallium arsenide, gallium nitride, cadmium sulfide are some of the commonly used semiconductors. The electrical conductivity of a semiconductor is between the conductivity of metal and that of insulator. So on the basis of conductivity, how you are going to define the conductor, insulator and semiconductor? So basically, conductor is what? The material whose resistivity is whose conductivity is very high and whose resistivity is low. Now how you are going to define the insulator? So the material whose resistivity will very high and conductivity will low. That's when both are opposite to each other, and you have seen the example of that, so you can easily understand this, that these both are opposite to each other. But what about the semiconductor? So how you are going to define the semiconductor on the basis of the conductivity and the resistivity of the material? So you are going to say that the electrical conductivity of a semiconductor is between the conductivity of a metal, that is conductor, and that of an insulator, which is a path conductor. The number of charge carrier in a semiconductor can be controlled as per our requirement. Their structure can also be designed to suit our requirement. Such materials are very useful in electronic industry and find applications in almost every gadget of daily use, such as a cell phone, a solar cell, or a complex system such as satellite or the International Space Station. Then see, this graph shows the temperature dependence of the electrical conductivity of a typical metal and a semiconductor. When the temperature of a semiconductor is increased, as you can see in this, its electrical conductivity also increases. So you have to keep remember, when the temperature of a semiconductor is increased, its electrical conductivity will also increases. The electrical conductivity of a metal decreases with increase in its temperature. So variation of electrical conductivity of semiconductors with change in its temperature is very useful property and find applications in a large number of electronic devices, and their classification of semiconductor can be elemental semiconductors like silicon and germanium, then compound semiconductor, that is cadmium sulfide, zinc sulfide, etc. And third, we are having organic semiconductors. So elemental semiconductors and compound semiconductors are widely used in electronic industry. So you can see here, these are some classification of semiconductors. Then next to that, we are having band theory of solids, a brief introduction of that. So first of all, let's see what is the band theory of solid. So basically, we begin with the way of electron energies in an isolated atoms are distributed. So as you can see here, according to the Bohr atomic model, in an isolated atom, the energy of any of its electron is decided by the orbit in which it revolves. So basically we know that electron revolves around the nucleus. It has its own orbit, but when the atoms come together to form a solid, they are close to each other. So the outer orbits of electrons from neighboring atom would come very close or could even overlap. This would make the nature of electron motion in a solid very different from that in an isolated atom. So inside the crystal, each electron has unique position, and no two electrons see exactly the same pattern of surrounding charges. Because of this, each electron will have a different energy level. Fine. And these different energy levels with continuous energy variations form what are called energy bands, as you can see in this diagram. The energy band, which includes energy levels of the valence electrons, is called valence band, as you can see in this diagram. If the lowest level in the conduction band happens to be lower than the now see, you can able to see the valence band. The energy band above the valence band is called as conduction band. See this one, this is the valence band, and the next to that, which band is there? This is the conduction band. So if the lowest level in the valence band, in the conduction band happens to be lower than the highest level of the valence band, the electron from valence electron can easily move into the conduction band. Normally conduction band is empty, but when it overlaps on the valence band, so electron can move freely into it. Okay, this is the case with metallic conductors. If there is some gap between the conduction band and valence band, so electron in the valence band all remain bound and no free electrons are available in the conduction band. This makes the material an insulator. But some of the electrons from the valence band may gain external energy to cross the gap between the conduction band and the valence band. Then these electrons will move into the conduction band. At the same time, they will create vacant. See, you can see this vacant place. So it will create vacant where other valence electron can move. Thus the process creates the possibility of conduction due to electron in conduction band as well as due to vacancies in valence band. So this is all regarding the conduction band, valence band and energy band of the solids. Then observe this graph. As you can see here, we are having insulator, semiconductor and conduction. So this is the energy band diagram. What you can say, this is the energy band diagram of insulator, of semiconductor and of conductor. So just observe the insulator energy band diagram of the insulator. So here, in this case, as shown in the diagram, a large band gap, that is Eg, exists. Okay, the gap between the valence band and the conduction band is called band gap, which is denoted by Eg, energy gap. So if this energy gap is greater than 3 electron volt, so this is the energy band diagram of the insulator, and therefore no electrical conduction is possible. Note that the energy gap is so large that electrons cannot be excited from the valence band to the conduction band by thermal excitation. This is the case of insulators. Then next case, this situation is shown in the diagram. Here a finite but a small band gap, that is, we can say that energy gap is less than 3 electron volt exists. Because of this small band gap, at room temperature, some electrons from valence band can acquire enough energy to cross energy gap and enters the conduction band. These electrons, though small in numbers, can move in the conduction band. Hence, resistance of semiconductors is not as high as that of the insulator. In this section, we have made a broad classification of material, that is conductors and semiconductors. Let's see the last one. So here this refers to a situation one can have a metal either when the conduction band is partially filled and balanced band is partially empty, or when the conduction and valence bands overlap. When there is overlap, electrons from valence band can easily move into the conduction band. This situation makes a larger number of electrons available for electrical conduction. When the valence band is partially empty, electrons from its lower energy level can move to the higher level, making conduction possible. Therefore, the resistance of such material is very low, or the conductivity is high. So this is the energy band diagram of the conductor, this is the energy band diagram of the semiconductor, and this is the energy band diagram of the insulator. So this is all regarding the conductor, insulator and